Our next speaker is Alan King. Alan received a BSc in geology from the University of Toronto in 1976 and an MSc in geophysics from Macquarie University in 1989. From 1976 to 1984, he worked as a geophysicist in exploration and resource development in Canada and Australia, Asia. In 1985, he joined Geophysicon Company Limited in Calgary, Canada, where he was involved in mining, geotechnical, oil sands, and environmental applications for a variety of commodities. In 1990, he was employed by Inco Exploration and Technical Services as a senior geophysicist, and in 1995 was promoted to manager of geophysics with responsibility for global exploration. With the takeover of Inco by Vale in 2007, he moved to Brazil to assist with Vale's geophysical work in Brazil and moved back to Canada in 2011. From 2009 to 2012, Alan was chief geophysicist for Vale Global Exploration, working on geophysical applications for base metals, iron, manganese, coal, and fertilizers, as well as target generation using regional and global data sets. Alan is currently working as a consultant with his own company, Geoscience North. His professional interests include the use of geophysics and new technology and ideas in exploration, mining, environmental, geotechnical, and other applications. Alan's very passionate about this topic. When I called him to invite him to be a speaker, he jumped right on board. He's a strong advocate of better 3D modeling, data integration, and analysis from prospect generation through to mining. Today, he will take us through a discussion on how 3D modeling, data integration, and analysis are the keys to enhanced exploration. Please welcome Alan King.
Yeah, thanks a lot. First of all, it's a real pleasure to be here talking to the Toronto Geological Discussion Group. I graduated from U of T and many years ago was running back and forth in front of these windows to my classes. And also, I was really keen, as was mentioned, to talk about 3D modeling. It's something that I've kind of quietly suggested for workshops for a while. And to my knowledge, there really hasn't been one for the mining industry. So I think it's a great venue, and it's a very rapidly evolving field, and I think we see a lot of papers on individual deposits and methods and stuff, but those are the details, and this is the stuff that hangs it all together, in my opinion. Yeah, why 3D? I've been a strong advocate for 3D modeling for a long time, along with a number of other people in this. And the reason is it's absolutely essential for good exploration. That's sort of the simple answer. But here are some of the reasons. I've maintained that all Earth science data sets are 3D, and in fact, they're 4D. We're often trying to solve the problem of time as well at the same time. It is by far the fastest and most efficient way to view data yourself and communicate 3D data to yourself or to your teammates or managers or investors. And we're talking about teams working together to work on geology, geochemistry, and geophysics. I think you have to be working in 3D to see everybody's data. The other thing, and this is sort of some of this is sort of comes over from the seismic industry, where we see a lot of as geophysicists, is that you need to avoid sideswipe. And those, I just call it unexpected negative effects from 2D simplifications. It was very famous in 2D seismic. It caused a lot of problems and a lot of dry holes. As soon as they went to 3D seismic, they turned around that terrible curve of increasing expense and decreasing discoveries that we see in mining. But in the equivalent in mining are out-of-plane drill holes that sometimes you see in sections where they're a bit offset, and the severe limits of 2D geophysical modeling of a 3D environment. It assists in QA/QC. I'll often come into a project that hasn't had a 3D model on it. I'll put it together, and all of a sudden I'll see a hole sticking up in the air. Or one that's 100 meters above the DEM, and it hasn't been seen in 1,000 drill holes because it's so hard to see all the data at once in section and plan. And those errors are mainly in positioning. And finally, as Ian was saying, I think many of the big future deposits, and I think most, and there's a lot of them, probably a lot more than we found to date, will be at depth. Because we'll just scratch the surface and will require very high level understanding of the Earth in 3D. I'm just going to start off with a brief and subjective review of the development of 3D modeling and mining exploration, because I think it kind of sets the stage for what we want to do. At first, everybody did 2D modeling in plan and section, and then there was a terrific development, which is 2D GIS, and I don't want to underestimate the value of that in our 3D discussion. And that was the main step forward there was the mutual positioning of all the data sets. So you got everything registered in the same space, in the same place. And that, we take it for granted now, but it's critical. And so we have to do that in 3D now too. The other thing was linked databases. So you've got multiple databases live to work with at the same time. You have topology there, which surfaces know what's on the other side of the surface, which is important for creating sealed models and calculating areas and volumes. And also the final one is analysis. Once you have all the data registered in 2D and 3D space, we have to come to some conclusions. And then 3D software developed and has since become the standard in the petroleum industry and other sciences such as medicine. And this really happened in the 80s and 90s, and the mining industry was a fair bit behind in this for no particularly good reason, I don't think. The technology was available, and we were seeing a lot of it at our conventions. And this is just an example, probably from the 90s, of a salt dome with 3D seismic. And this is virtual anatomy based on somebody's 3D Vision, 3D imaging software. So other industries are doing this now, and we better get on the ball pretty quickly. Here's some of the 3D exploration initiatives by the mining industry since the 1990s when this started to gather momentum. And this is just speaking mainly for North America and Europe, where I was residing at the time. Most of the major companies, I think, realized the urgent need for this. Noranda, and was John McGaughey in particular, who has since got on board with GOCAD, which was a very high-level 3D modeling package developed by a consortium of oil companies. It was developed in Nancy in France, and it was by far, the Cadillac of the industry at that time, and not very accessible to the mining industry, and Mira has done a lot to change that. Rio Tinto Exploration, the UK, did the same thing. They built a 3D package built on the Intergraph 3D modeling software. Unfortunately, that's no longer supported. And our company, Inco and Vale, developed an in-house package developed largely from scratch by University of Waterloo students. And finally, as Ian's been talking about, Geosoft has been expanding the Oasis montage and all its wonderful importers and exporters and large data handling capability into 3D. Now, in Australia at the same time, NCOM added the Discover 3D add-on to MapInfo. Intrepid, another geophysical company, in collaboration with BRGM, which is the French Geological Survey, built the Geamadeller 3D package, which is a rapid 3D model builder. And then finally, fairly recently, a company called Leapfrog from New Zealand is making great strides. And they use something called radio basis functions that do very, very rapid geological modeling. I'm not sure how much data, geophysical data, they incorporate into that. Here's some other 3D earth science software packages of interest that I found, and I sort of keep my eye out for these things. There's something called ParaView Geo, of all things. It's a spin-off from the ParaView 3D software. This was developed at Sandia Labs in the US for modeling, I think, hydrogen bomb explosions, and it works on everything. There's no data that can stop this program. It's free. It's fairly user hostile. But much to my surprise, a group associated with Laurentian University called Morocco built a geological application for that called ParaView Geo, and it's free and it's on the web, and it does most things, and it's very powerful. Now, I hadn't really seen anybody using it until we went to Bingham Canyon, and Rio Tinto was using it in their 3D immersion room there, and there's also a couple of contractors delivering data in that software as well. The other one that I found that's really interesting is this one, the UNAVCO Geon IDV. The U.S. has this huge Earth scope project where they're imaging the whole continental U.S. in 3D to depth of hundreds of kilometers. They got the U.S. Informatics industry fired up, and they spun off from the U.S. Weather Services Integrated Data Viewer a full global solid Earth modeling system, and they basically just took the weather software, which does terrifically complex 3 and 4D models, and they let Z be negative, and they had the Geon IDV. And that's available, and that's free. The conventions are quite different, again, not particularly friendly to people in our business, not very good importers and exporters. Google Earth is really useful. It's 3D, and it was really a lot of people's first exposure to 3D and DEM models, and that you can put any data on top of Google Earth. And I don't know if people have seen it, but I've seen people doing structural geology on Google Earth surfaces, and there are global data sets available for free on that surface, and it's actually pretty useful for a lot of things. And finally, there's this other really interesting software here called MOVE, and that's structural geology mapping program from a company in Scotland that is very, very specialized and I think fairly expensive for complex dynamic structural modeling. The other thing I wanted to mention, when I've been thinking about this for a while and wondering why we really have been a little bit slow getting onto this, we're not alone in this, in our problem of 3D visualization. As a matter of fact, we've got lots of company. And I believe that the best value is not reinventing the wheel, but collaborating with other industries. We've talked about the oil industry. They had really high quality packages in the 80s and 90s. They were very expensive. The scientific and medical industry has ParaView 3D. The petroleum industry has a number of existing, traditionally very expensive packages, but just recently there's been a couple released for free. One called OpenTech, which they're all seismic 3D packages, but they're surprisingly powerful. And another one from Australia called DUG, Down Under Geophysics. They're totally devoted to the seismic industry, but they're kind of interesting to look at if you're interested in this field in general. The petroleum industry has for years faced the same images with much bigger data sets, much more detailed data, a lot more geophysical logs, but much simpler geology. And they have what was called, I'm not sure what the status is now, but they had the Open Spirit Initiative, which was a consortium of companies developed to work through this whole problem of connecting data to applications. And their sort of schematic I've seen for them was that there are a whole bunch of databases down here. There's a whole bunch of applications up here, and you've got middleware in the middle that serves data up to, by changing their coordinates, getting them in the right format into these things. And it's kind of an interesting model, and you can go check out the Open Spirit website. I think it's a private company now. And finally, and this one took a while to occur to me really, but movie animation. We take months to make a 3D model sometime. And if you go watch Toy Story, they do a fully rendered complex 3D model 30 times a second, or maybe 50, I don't know what it is, and they do it for 3 hours. So there's enormous 3D modeling capability out there, and they manage the data sets, they do the illumination, they do the surfaces, and they manage all those things pretty effectively. And when I was looking for an example, I looked at Toy Story, and then I found out they've already done Continental Drift with Ice Age 4. So anyway, I think those are groups we can look to for ideas, particularly about data management and some of the routines we look for visualizing things. I'm not going to go through all of this, but this was just a list that and this hasn't changed much since the mid-90s, of what a general purpose exploration 3D scientific geographically enabled environment, what should it consist of? And I've just added a little asterisk here that now, and it probably involves multiple software packages. We're probably not ever going to get all this in one place. It'd be nice if we could, but different packages evolve at different paces. So you're often working between multiple data packages, and of course that gets you to the crawler to that is we need really good importers and exporters to move back and forth quickly. You want to import data. You want to handle all data types. The key one that Ian mentioned is data integration and the critical need for data coordinate transformations on the fly. If you're doing these models, they can be incredibly time consuming. If you have 100 data sets in 50 different coordinate systems, and you have to transform all those into the same coordinate system and do it correctly, it's a really hard subject. It's probably the hardest. It's harder than the geophysics, I think, projections. You want data visualization in many formats, 2D, section, plan, full 3D. You want to be able to operate on individual data sets. You want to do things to them, but you also want to be able to do operations between data sets, and you want to be able to export data, operate on it with an external software, and then bring it back in quickly. Topology is important. I had to look up the definition. But these are, and my rough one is that surfaces know their relationship with their neighbors, and this is essential for creating sealed 2D areas or 3D volumes for volume calculations. If you're creating 100 volumes in a gigantic model, and there's a little tiny leak in the corner that's a micron across, your volume calculation will leak out through there. It's a shocking thing to have happen. It's very hard to track down. And you want the ability to create new objects based on data integration, or to draw it from scratch in 3D, which is very difficult to do. And this is actually another part of a limiting thing. Like, you want a free-form draw in 3D. That's a fairly hard thing to do still. You want to do data analysis critical, and I just put at the bottom, but we tend to forget about geostatistics and its important role in linking all this stuff together, but that's another subject for a geostatistician, not for me. I'm going to talk about some examples right now. And I'm going to go from global to microscopic. And I think what the main point I want to get to, the details are kind of irrelevant, I think, but the issue of managing and understanding data at all these scales. This is an example of the Pacific Plate dipping under, here's North America, here's the Pacific Plate dipping under here. It's called the Farallon Plate for some reason out here, and you can see it right, it extends right under to the East Coast. These are the mantle plumes imaged by global scale earthquake seismology of the Earth, and it seems kind of theoretical at the moment, but it's not. For our global project generation, we were using models like this to look for porphyry coppers along those subduction zones and where the breaks and those things happen. And this is 3D regional project generation. We've talked about 2D, but you really need to think about 3D, where the big hotspots were, where the plates are, if you want to look for big deposits undercover. And that's just the gravity of the Earth in Google Earth. This is a great example I've shown a couple times. This is Geoscience Australia, as was pointed out. They're serving up statewide 3D models now. This is the 3D geology of Tasmania, served up in virtual reality markup language on the web. So I think all state surveys should be producing their models. This is just another quick example, but this is from the Australian National University, and they've got a project called the 4D Tectonics project. And again, you can look it up on the web. It's a private consortium supported by a number of companies. They have some papers, but they're quantitatively modeling mainly in Southeast Asia, the plates in the area. They're much more complicated than maybe we should expect. But and they're, a lot of people have tied the location of the biggest porphyry copper deposit to significant breaks or bends in these slabs. So it's actually directly relevant to exploration. So getting down to camp scale, this is the Sudbury 3D model from integrated data. This was done in the mid-90s in GOCAD. We did it internally with a lot of support from Mira. It took 2 man-years. The work has come a long way since then, and there's people have workflows and rapid modeling. And the other issue that comes up here is that creating 3D models has taken too much time. You don't have time actually to create it while you're working on the project. So we have to get that down, and it's happening now. And this is just the kind of an example of the data volume you need to handle for any 3D model. This is the Sudbury Basin outline here, and that's the historical surface drilling. And in the Sudbury Basin database, there's 160,000 drill holes down to 3 kilometers deep. And if you just turn on in your 3D database that's connected to the 3D model, you just turn on the copper nickel, you can immediately see new targets. I mean, you just go to where the end of the mineralization is and the geology is still there, and you can just see them, ore bodies and potential disappearing off to depth. So 3D really, really accelerates the process of exploration. This is just another example. The biggest data sets we've got now in exploration are the 3D seismic data sets we're getting for hard rock, fertilizers, potash, and coal. They're terabyte data sets. This is just an example of we did a 3D survey here over on the west range of the Sudbury Basin. That was done by Bert Melkwright and some people from U of T. And this is the 3D surface with the ore body at 1 kilometer down and the scattered ring from the ore body. This is starting to, this is another camp scale example from the Thompson Nickel Belt. We surveyed the whole belt. This is 2 kilometers vertical, and these are 2D sections showing the conductivity to depth. And this is enormously valuable for structural modeling at Thompson, which is one of the key problems in that area. There's lots of barren sulfides, and the key is locating the structures that are more favorable for mineralization. This is starting to show some integration now. These are the 2D sections of conductivity to a depth of about 2 kilometers from magnetotellurics, and superimposed on there is a point cloud from 3D mag inversion. So we're looking for places where there's significant conductivity close to very magnetic mafic and ultramafic rocks, and then working up some structure, giving that to the geologists and helping them with their structural geological. The next thing I wanted to mention briefly was imaging whole mineralized systems. There's a terrific advantage to seeing the whole system. Mineralized systems for big ore bodies are large. They're much larger than the ore body itself. Porphyry copper system is typically a large area of alteration containing a lot of barren pyrite, and the copper tends to be concentrated on the inside core. And if you just do a line across here or a line across here, you're not going to know what you're looking at. You're just going to see a small piece of it. Imaging whole systems again. We want to see the whole systems in 3D. This is from a recent case history by the Quantec Orion system from the Santa Cecilia deposit in Chile. Here's the lithocap. Here's the main porphyry alteration system. Intersections of copper through here, and these are likely for the first time ever seeing roots of porphyry. And this isn't a 2D, this isn't a 3D example, but I just wanted to put it in to show you what's happening for imaging whole mineral systems. This is the magnetotellurics over Olympic Dam, and here's the world's biggest IOCG right here. And look at the conductivity anomaly extending down from there that just points right up at the deposit. So large-scale crustal imaging with mag gravity and MT is direct vector to targeting the largest deposits, and it can be completely blind, and a lot of them will be. This is just an example of some of the 3D work complexities, and the reason we got pushed into 3D in Sudbury. We didn't have a choice. These are all drill holes, so we do borehole EM and all those from multiple loops with 3 components in each hole. It's not physically possible to manage that in 2D, so we have to work in 3D around these deposits, and we mesh them into 3D sheets like this. The next slide just shows some recent data collected with the new Sintrex borehole gravity probe. And I'm just putting this in to show how important integration is. Ian pointed out that individual data sets are not, the solutions are not unique, but if you start putting together multiple data sets, and the theme is integration, you can start reducing the ambiguity a lot. If you have an off-hole conductor, it can be graphite, it can be barren sulfides, it can be thin sulfides, but if you have a gravity survey that shows you the density and gives you the tons, you've got a lot more to work with, so that the gravity survey can hang the tons on an EM conductor. And finally, this is an example of everything tossed in together. This is an example of Kelly Lake in Sudbury. We're looking at a borehole EM survey with a 3D vector showing the direction of the EM field in the hole. These are grades in the hole. This is a plate interpreted off the hole with a degree of confidence color-coded on the plate. And we're looking up at the bottom of Kelly Lake here. And my office used to be, I'm not sure which side room, but I think it used to be right over here. I put in a couple of seismic examples because we tend to forget those, and it's becoming a more common part of our work. They're gigantic data sets. They're very high resolution. We need to be prepared to handle those in our 3D modeling. This is just from the best hard rock 3D reflection I've ever seen. It's for PGE targets in the Bushveld. Here's the Marinsky Reef in red, and here's a nice seismic reflector from a half-meter thick zone down 800 meters. And that's a plan view on the UG2 reef at about 800 meters down. So again, these are 2D images from a 3D seismic volume. The other one that we did a lot of work in, and it generated some of our very large data sets, fertilizers are mining too. I think some people forget that. Potash is a pretty good business to be in, even if the price is a little low. This is just a 3D seismic survey for potash from Western Canada. It shows about 2 kilometers by 2 in plan view. This is actually a time slice about 1 kilometer down. This is a hazard area where there's been some solution of the salt, and if you mine into there, your mine might fill up with water. And this is actually the mine entry imaged with the seismic. The next thing I'm going to do, I'm moving down from global to camp scale, and I'm just going to talk a little bit about detail stuff, and then we'll try and get into some conclusions before I run out of time. You can, as you get closer to the mine, we've got very high resolution imaging techniques, which would work in 2D panels, and then you can put them together into 3D. This is cross-hole seismic imaging from a parrot hole in the middle to 3 holes around it from the Free Brook zone at Voisey's Bay, and where the low velocity red zones show massive sulfides. I wanted to put this in because this is the kind of detailed information you should be dealing with in any model, particularly if you're going to create structural interpretations. This is optical televiewer. I think most of you have heard of this, but this is not core. This is a virtual core taken by a camera going down the drill hole. This spins sometimes when it's connected to the AVI, and the thing I want to emphasize for this is that core is oriented. So one of the biggest problems in structural geology is orienting your core. You've got many solutions if you've got hundreds of drill holes with unoriented core. So either oriented core or these televiewers, you can start doing much more reliable and less non-unique interpretations. Now, how do you use that in a 3D model? This is an example from our in-house software where you've taken a drill hole, which would normally just be a cylinder of some kind, and you actually take the televiewer file, which is 100 megabytes. You expand the drill hole to a cylinder, and you can paint the televiewer image on that. You could bring in a digital interpretation of every fold axis and every planar feature in there on little active planes that you can pull out and push in again. And finally, getting down to the microscopic scale, this is some work that's been done fairly recently, and it's using 3D X-ray computed tomography on core and on rock. And so we can see within individual rock specimens now. We have 3D imaging of structures inside and the distribution of sulfides inside the core, which can be an oriented core, gives you microstructures for structural interpretation. So you go right from global to to microscopic. We have a problem. We have way too much data. I think anybody who's tried to do this and tried to keep all this stuff present in their head realizes we have 50 layers of geochem data, hundreds of layers of geophysics. This is just from the main block at Voisey's Bay in 2005. Hundreds of data sets, and I'm sure that's doubled or tripled by now. The solution is more automated, the software that can handle more complex problems, integrated modeling, and full systems that do 3D inversion and imaging. Now, I sat down and I tried to make a chart of the evolution of 3D modeling through time. And I put geophysics, geology, and geochemistry at the top, or drill hole logs. And I started to try and show the interaction between them as they come down. So we started with manual forward interpretation, as Ian showed, and we're now here at the bottom where we've got full implicit geological, geophysical modeling with multiple data sets. We've got 3D simulations and simulations with geophysical constraints. And we're about here right now, and we have to get to here. And I'm not going to read through all that, but I'm happy to supply a copy of this to anybody who's interested. The key to improve models and exploration efficiency is full data knowledge and data and knowledge integration. And knowledge includes everything you know from articles and models of deposits, I think. And you need all geology, structure, geochem, geophysics, and knowledge together. And if you take, often one of these will be ambiguous, and two, sometimes a bit better. But if you put three of them together, you can actually arrive at often unique solutions, surprisingly reliable. So the reliability goes up the more data sets that you look at. The current best practice is implicit integrated geological and geophysical modeling in 3D. This is just, it's being done by the Intrepid Geamadeller software or the Skua package from GOCAD Paradigm. It does geological modeling automatically. You give it geological maps, drill holes, it builds a 3D geological model. Then you give it the geophysical data, and it fits all the geological and geophysical data sets at once. So it honors all the data automatically. Now, and you're allowed to intervene anytime you want to fix things up that get a little silly. I'm just going to flip through those examples. This is just the kind of things that are being contemplated for this. This is from the Australian Academy of Science, where they sat down and said, how are we going to ensure resource discoveries for Australia for the future? They got the smartest people in the country together, and they proposed 6 initiatives. One of them is a national map of the deep crust and upper mantle in 3D, and the national 4D metallogenic map. So that's a metallogenic map that goes back to the beginning of time in Australia in 4D. The issues, I'm not going to go through these all because I'm just about out of time. We have big data. Data management is a huge, critical, and often neglected issue. 3D modeling has been painfully slow. We need to automate it. The human brain can't optimize all these data sets. Mine's worn out. We have a lack of explorationists trained in 3D software. Access to software has been problematic. I don't think there's any undergraduate university level program training in 3D. I just see 2D GIS now. I think this should be compulsory in 3rd year. And we need to combine many disciplines. Teams and individuals need to master many disciplines together. The future, I just have a proposal that all geoscience data should be presented georeferenced in 3D, including all academic articles. A paper is irrelevant, like paper's 2D. And we get 2D articles in digital form. Like, why not serve it all up in 3D with all coordinates on it? Imagine if every article opened in 3D, and we slice sections out of it, and we paste it back into our 3D models. I think we should think about 4D modeling. The software is available, and I think we should increasingly be thinking about artificial intelligence assistance to help mine these growing mountain ranges of data for knowledge and targets that's significant. That's a very good question. I use Geosoft and GOCAD together right now, and and AutoCAD. Sorry, not AutoCAD. ArcGIS for 2D preparation, quick modeling interpretation, data transformation, and then full-blown GIS 3D inquiry.